Here are a few properties of integration that are important. We'll consider this first one in this video, and then we'll follow up on these others. This first one is very important. It's for indefinite integrals, but what it says is that if you take the derivative of an indefinite integral, you get the integrand. So it makes sense because remember, this antiderivative is the when you do the indefinite integral, you get this antiderivative, and when I take the derivative, I get f prime plus 0, and the antiderivative gives me f. This is an antiderivative of f, so when you take the derivative, it gives you f. So we've kind of talked about that, and then this is kind of going the other way. It says when I want to do an integral, I want to write down the antiderivative of this integrand. In other words, I want to write down what I take the derivative of that gives me this. Well, I take the derivative of f to give me this integrand. So that's another way to say the integral and the derivative cancel each other out. So in both these cases, if I take the derivative of an integral, I get the integrand. If I take the integral of a derivative, I get the function back again. So differentiation and integration are sort of these inverse operations. Not the same as like square root and x squared. Those are function operations, but these are calculus operations that one of them will undo what the other one does. So let's look at a couple of examples how to use that. This first example, I've got the integral of the derivative of this mess here. I have no idea how to integrate this. I definitely don't want to take its derivative because it's going to make it even worse, but I don't have to. When I see the integral of a derivative, then all I get is secant tangent x squared plus 1. And since I'm integrating, I do have to put the plus a constant, because remember, the indefinite integral always has a plus a constant on it. So very nice that it'll just cancel out. The integrals always cancel out derivatives. Derivatives always cancel out integrals. We can use that to help us evaluate a few integrals, and it's actually the basis of a lot of what we do going forward. So here I've got something I want to integrate, and this is not in my list of things that I know what the antiderivative is. So I can't just, I want to try to manipulate it. You might say, well, go ahead and factor, but that's not going to really fix anything. I'm going to use the property that I just brought up. I'm going to recognize that this is actually the derivative of something, and then I'll have the integral of a derivative. So I got to figure out what kind of thing would give me a derivative that looks like that. Now you might look at each piece separately, but look at it all together. When do I get two terms coming out of a derivative? It comes out of a product rule. So if you look at this carefully, what I've got there, someone took the derivative of x squared e to the x. Because if I do that, the derivative of x squared e to the x, I take the derivative of e to the x times x squared plus the derivative of x squared times e to the x. There's your product rule. But once I can recognize it's a product rule and rewrite it in that notation with the derivative inside the integral, we know that the integral is going to wipe out that derivative, and I'm just going to get the x squared e to the x plus a constant. You can always check yourself, remember, because I can differentiate this to see if I get this integrand back. Well, the derivative is e to the x times x squared plus 2x e to the x plus 0. So it's not always easy to see that. This one wasn't too bad. Sometimes what happens when you use a product rule, you factor or you combine things simplify, and you lose the form of the product rule. So this is only works in limited situations. Here's another one. Again, this is not in my list. I can't do any easy manipulation to turn it into something in that list of antiderivatives. And so I've got to try to recognize that this is some sort of derivative that was applied. And so what sort of things would give me something like that? Well, what you should recognize is there's an x cubed and there's a 3x squared. That 3x squared looks like the derivative of that inside function. So it looks like somebody took a chain rule here. And that's actually what it is. If you take the derivative of, well, let's see, I'd have to be taking the derivative of sine x cubed. So I did a little bit of work in my head there, because I could see if it was a chain rule, I'm looking for something of this form. So this would be my g prime this would be my g on the inside, but this cosine would need to be f prime, meaning the derivative of something. Well, that's the derivative of sine. So putting it all back together, then the derivative, that is the derivative of that composition of functions. So putting it back together, I would need an x cubed on the inside of a sine, because now I can check that that does actually give me, when I take the derivative of this, I get the derivative of sine, which is cosine. Put the inside function back in and multiply by that derivative. So anytime you can do that, you can evaluate the integral. Whether it's a definite integral or indefinite, you can do this. With a definite, then you just plug in the limits of integration. With the indefinite, you just stop by putting plus a constant. So if you can see it, do it. But we will have some techniques for one, like this in particular. We will have a technique for still being able to do this. But this is a nice shortcut. If you can see that it's an actual derivative, then write it as a derivative. Then the integral and that derivative cancel out, and you get a nice quick answer.